Okay, so hi, welcome to this next video on linear programming. So we are still working towards our goal of viewing what the simplex algorithm is doing from a geometric point of view. And so on our way to that, we are going to be talking about the most important geometric feature of polyhedra that we will need, which is that of extreme points. And so that is the topic of this video. So extreme points are actually something that can be defined for any convex set, not just polyhedra, but really all we'll need it for is in the context of polyhedra. So intuitively, what we're going for when we have the idea of an extreme point, what it's supposed to be is a quotes corner point of your convex set. So here's some examples of some convex sets, and only the left one is a polyhedra. The other two are not. But I've highlighted in red what the extreme points are for each of these. For example, this left one, this triangle here, the extreme points of this polyhedra are exactly the corner points. It's literally what they are, and then the extreme points for these other two, for the ellipse, it's all infinitely many points around the boundary that's curved here, and then for this hybrid thing, it's got a curved part and some straight line segment parts. The extreme points for the curved part, it's the entire curve, including the endpoints, and then for the straight line segment parts, it's just where they meet at that corner there. That corner is also an extreme point. Okay, so that's the idea of what it's supposed to be, but formally what it is that it is a point that cannot be realized as being on the interior of any line segment inside this convex set. So take any of these convex sets. Let's just take the polyhedra here, the polyhedron here, and this triangle. And for example, this red point, this bottom left one, this corner is an extreme point because I cannot find any line segment inside this triangle such that this point is on the inside of that line segment, is on the interior. So try as you might, take any line segment contained in this triangle. There, for each of those line segments, this point will either not be in the line segment at all, or it will only be an end point of the line segment, but it will never be strictly contained inside of it, inside of the line segment. And that's similar to how it works here. It's the same definition, same reasoning applies to make all of these red highlighted points extreme points of their respective convex sets. Why does this idea fail? For example, if we take a point like right here on the edge of this triangle, why is this not an extreme point? Well, because I can realize it as being on the strictly inside a particular line segment inside this triangle. So let's just take this point and then go a little bit to the right and a little bit to the left, and then that line segment that you get then will strictly contain that point on the inside of it, and so that point is not extreme. And that reasoning applies for every point along this edge, except once you get to the corner. Because once you get to the corner, you can't go a little bit to the left anymore, and there's no other direction you can travel in to make this strictly contained inside a line segment. So I can write it so that it's the end point of a line segment, but that's not what we're concerned with here. We're concerned with it being strictly contained on the inside, so it's not one of the endpoints. So that's what makes these red points extreme points, is that they are not strictly contained in any line segment, which is itself inside the convex set. Okay, so why do we care about extreme points? The question we're going to pose is that, well, is there a relationship between extreme points and basic feasible solutions of linear programs? So that's just kind of coming out of nowhere, seemingly. Why would there be a relationship here? But in fact, there is a relationship, and it's very strong. Our goal is the following. It's actually to show that extreme points of polyhedra and basic feasible solutions of linear programs are the same thing, in fact. So, if you give me a linear program, and then I look at the basic feasible solutions of that linear program, and then I look at the associated polyhedron for that linear program, the feasible region, the basic feasible solutions geometrically on that polyhedron are the extreme points of that polyhedron. And And then, vice versa. If I look at the linear program and I look at the associated polyhedra, and and I just look at the extreme points right out of the gate of that polyhedron, then those extreme points are the basic feasible solutions uh, of the linear program. And so, and we know that the simplex algorithm iterates over various basic feasible solutions of the given linear program. And so geometrically, what that is corresponding to is that on the polyhedron, it is iterating over various extreme points of the polyhedron. And so the corner points, remember, is what we're going for there. So it's iterating over various corner points. And, and so that is the entire main geometric idea of what the simplex algorithm is doing. We need to show how this actually can be established. That's our main overall goal. But in this video, we're going to have a more modest sub-goal, which is to it's going to be give a preliminary characterization of extreme points. So we're going to develop a test for whether a point is extreme or not, besides whether it meets the definition. So a test for it, and that'll characterize what points are and are not extreme, so that we can establish this relationship between extreme points and basic feasible solutions. And so, this characterization will be in this video, and this will be in terms of tight constraints, which is why we did a video on tight constraints first. Okay, so this is just formally writing down the definition of an extreme point. So if you give me a convex set C in Rn and a particular point x bar in C, that point will be an extreme point of C if it cannot be realized. So let me emphasize the not there. If it cannot be realized in this particular way here, if I cannot write x bar as lambda x prime plus 1 minus lambda y prime, so linear combination of x prime and y prime for some particular points, x prime and y prime, that are also in the set C that are distinct, and lambda is strictly between 0 and 1. So remember, if I let lambda be a parameter that ranges over the whole interval 0 to 1, including the endpoints, then this right-hand side, when you let lambda vary, is the entire line segment from x prime to y prime. That's what this is. And so when we're here restricting lambda to be strictly between 0 and 1, the point on the right-hand side here, this accounts for points that are strictly contained inside the line segment from x prime to y prime. So it's the x prime and y prime are the endpoints, so it's all the other points inside that line segment. And so if x bar can be realized in that way, then it is not extreme. But so that's our definition then. So x bar is extreme if it cannot be written in this way. So in other words, x bar is an extreme point if it cannot be strictly contained in any line segment in C. So it's important that the line segment is itself in the convex set C. Okay, so that definition is for any convex set. We are going to be focusing on the extreme points of polyhedra specifically, not just of any convex set. So we can characterize extreme points of polyhedra in terms of tight constraints. So tight constraints were introduced in the previous video, but just so that everything is all in one place, I'll just briefly go over that again. A tight constraint is that when you give me a feasible system of linear inequalities like this, ax less than or equal to b, and an associated feasible point, x bar, so it satisfies all those constraints, then look at the constraints which are, it satisfies all of them, right? So just split it up amongst the constraints that are satisfied with strict inequality and exact equality. And so a particular constraint is going to be said to be tight for x bar if when you plug in x bar here, you get exact equality. So that is what a tight constraint is, and sometimes it's also called active, by the way, just because in a sense, if x bar meets this less than or equal to with exact equality, then in a sense, if you went any further in some direction, you'd cross over to the other side and violate this inequality so that it doesn't hold anymore. It's not less than or equal to, and so in a sense, this constraint has been activated because you can't go any further. And so anyways, you can call it whatever you want. You can call it tight or active. They're both kind of used, but we'll stick with tight for the most part. So yeah, so again, just the idea is that if I have this system ax less than or equal to b, that's all the constraints here for all the rows, then take a particular point x bar here and then look at which constraints hold with exact equality. So x bar satisfies everything, but which ones does it satisfy with exact equality? So those are the ones that you call tight, and so I've highlighted whichever ones those would be in green here. And here's an example which will be relevant for us in the future characterization that we'll be doing in just a few moments. So it's the same linear program that we've been recycling over and over again. If we take the point x bar to be 1, 2, so 1 over and 2 up, I know that at this point it looks like it's shifted to the right of 1 a bit, but that's only because I'm bad at drawing. That's not for any fundamental reason. It really is the point 1, 2. And so if we start with that point, then the tight constraints are the ones that hold with exact equality. Geometrically, you can see that this point lies on two boundaries, two hyperplanes, right? So hyperplanes are lines in two-dimensional space. And so it lies on this line and it lies on that line. And so the associated constraints for those lines are the ones that will be tight. And I've highlighted those here on the left. So it's this line going diagonally downwards is this first constraint that got highlighted, and then this line that's going, this horizontal line here is corresponding to the third constraint, and those are tight because it lies on the boundary for both of those. And algebraically, you can verify that when you plug in x bar for those particular constraints, you get exact equality. So if I plug in x bar here, I get 1 times 1 plus 1 times 2 is 3, and that's exactly equal to the right-hand side. And similarly, 0 times 1 plus 1 times 2 is 2, which exactly equals the right-hand side here. And then for these other three constraints, you can plug x bar in, and you'll see that they still hold with less than or equal to, but they hold with strict less than, not equality. And that's corresponding to the fact that this point x bar is not lying on any of these other three boundaries. So it will not make any of these constraints tight. So the tight ones are highlighted here. And then, so this notation came from the prior video. A equality is the submatrix of tight constraints for x bar. So you give me the point x bar, and then I look at which constraints are tight, and for the matrix part of it, which is here, I just smush those rows together, and for the vector part of it, I just kind of smush those two components together. So here, A equality will be the two highlighted rows here, so 1, 1 and 0, 1, and so that's what we get here. A equality is 1, 1, 0, 1. And B equality is 3, 2. That's the 3 that's highlighted and the 2 that's highlighted. Okay, and so I didn't just throw this example in for no particular reason, since we already did a video on this. I picked this point specifically because it's not just any point, it's an extreme point of this polyhedra. And so we are going to be establishing a relationship between extreme points and something regarding tight constraints, which we'll say in just a moment. But we can see that this x bar is an extreme point visually because, it's a corner point of this polyhedra, and you can see that so because it's a corner point, then there's no line segment inside this polyhedron that strictly contains this point. Yeah, and by the way, just remember that by definition of what A equality and B equality are, we have that A equality times x bar equals B equality. So this equality holds because by definition of what A equality and B equality are. So that was covered in the prior video as well. Okay, and so what's the characterization for extreme points then of polyhedra specifically? This isn't a characterization of extreme points for any convex set, but specifically for polyhedron. Okay, so what is it? Well, if we take our polyhedra to be the set of points that satisfy some linear system of inequalities, that's our polyhedron, and let x bar be some particular point in the polyhedron. So in other words, it satisfies all these inequalities. Then also, what you do, so now you have this point x bar, so take A equality to be the matrix of tight constraints that's associated to this point x bar. So the relationship that we now have, how can we test whether x bar is an extreme point or not? Well, here it is. x bar is an extreme point of the polyhedron if and only if the rank of that matrix of tight constraints is equal to n, where n is the dimension of space that we're living in here, this n. It's also the number of columns of A and of A equality. That's the same number. Yeah, so remember, A equality is a submatrix of A, and then it has just as many columns as A did as well. And the number of columns is n. So the rank of this matrix is at most n. So if the rank is exactly n, then that means that all the columns of A equality are linearly independent. So in other words, we can say that the matrix has full column rank. So anyway, so x bar is an extreme point if and only if the rank of A equality is n. So we can take a look at how this works in practice with the example that we just did above. So we took the point x bar to be 1, 2. It was that corner point, and the associated matrix was this 1, 1, 0, 1. And so visually, we already verified that this is an extreme point. So we should have that the rank of this matrix is the dimension of space, which is 2. And so the rank of this matrix is 2, which is equal to n, the dimension of space. It's also the number of columns, all the same number, n. So the rank does meet that number 2 in this case. And we can just see that this has rank 2. So that by this test, assuming this test is true, which we'll prove in a moment, then that shows that x bar is an extreme point. Now, on the other hand, what if you took the point x bar to be 0, 1 above? So let's just take a look visually at what would be happening at the point 0, 1 on this example. So 0, 1 is this point right here, and you can see that this point should not be an extreme point because it's not a corner, right? And you can see that if you go just up a little bit and down a little bit, then that line segment is inside the polyhedron, and it strictly contains the point 0, 1. So so like 0, the coordinates would be like 0, 1 plus epsilon, and 0, 1 minus epsilon for some very small epsilon, and that would work to show that this is not extreme because it is contained strictly inside some line segment which is in the polyhedron. Anyways, okay, so that's visually what's going on. Now, by that test, can we also verify that this is not extreme? If you look, this point lies on just one hyperplane, right? Just one tight constraint here because of the one hyperboundary that it's lying on. And so which constraint is that? Well, it's the one that says that x1 needs to be greater than or equal to 0. Or in other words, negative x1 is less than or equal to 0 because everything is a less than or equal to constraint. So that's this fourth constraint here is the only tight constraint for this particular point 0, 1. And so then the matrix A equality in that case is just a one row matrix. There's just one tight constraint, so it's just this one row minus 1, 0 is the matrix. So if we go back down here, that is what we've written. So if we took x bar to be that point 0, 1, then A equality is just that one row. It's minus 1, 0 of the matrix. And so so the rank of this matrix is, well, it's just one row, so it's a rank 1 matrix. And that's strictly less than n, so it's not equal to n. And so then by this test, that says that x bar is not extreme. And again, so this all agrees with what we already know. We can visually verify that at 1, 2 is an extreme point and 0, 1 is not, and then it's agreeing with this test of regarding the rank of the matrix of tight constraints for these points. Okay, so that's the characterization that we have for this video. So let's just prove this, and then the proof will actually give us a little bit of insight into what we're able to do in order to explicitly show a point is not extreme. So we'll just be able to view things with just a slightly different perspective once we finish this proof. So, there's two directions to show for the proof. We need to show that if x bar is extreme, then the rank of A equality is equal to n, and then the converse as well. If you start by assuming that the rank of A equality is n, and show that x bar is in fact extreme. So we need to do both of those things. So we'll do that latter thing that we just mentioned first. So we'll assume rank of A equality is equal to n, so let's show that x bar is extreme. So that's our assumption, rank equality is equal to n. So let's go by contradiction then. Let's assume by contradiction that x bar is not extreme. So if it's not extreme, then we just use the definition of what extreme means, or the opposite of extreme in this case. So that means there do exist points x prime and y prime in the polyhedron such that, or the polyhedron, by the way, it's just a set of points that satisfy this linear system of inequalities. So there's two distinct points in this polyhedron such that x bar is strictly contained in the line segment from x prime to y prime. So that is, x bar can be realized as lambda x prime plus 1 minus lambda y prime for some lambda that's strictly between 0 and 1. So x bar is strictly contained in the line segment from x prime to y prime, where that line segment itself is inside the polyhedron, because we know that polyhedra are convex, of course, so they contain their line segments. Okay, so we're assuming then that we can write x bar in this way. So what does that give us then? Well, B equality, we know that that equals A equality times x bar. That's just by definition of what A equality and B equality are. These are the tight constraints for the matrix of tight constraints for this point x bar. And now we just replace x bar with what we're claiming we can write it as, because we're assuming that x bar is not extreme. So we can write it x bar like this, lambda x prime plus 1 minus lambda y prime, and we can just distribute A equality inside the addition here. And then you get these two terms. And so we have lambda times A equality times x prime plus 1 minus lambda times A equality times y prime. And so the lambda and 1 minus lambda, they're both strictly positive things, because lambda itself is strictly between 0 and 1. And then A equality times x prime and A equality times y prime, they are both less than or equal to B equality. Okay, so why is that true? Well, just for x prime, let's take a look. A equality times x prime, remember, we are assuming that x prime is a point that is inside the polyhedron, which means, by definition, that x prime satisfies all the entire system of linear inequalities here, so all of them. So A times x prime is less than or equal to B. So in particular then, because A equality is just a submatrix, and that corresponds to just the constraints that are tight for x bar. Now x prime is not the same thing as x bar, but nonetheless, this is just some of the constraints. A equality is corresponding to some of the constraints. And so, but we know that x prime satisfies that it's less than or equal to B for all constraints. So in particular, for the tight constraints for x bar, we know that A equality times x prime is less than or equal to the corresponding right-hand sides, which is the B equality components. So that's why that's true. And the exact same reasoning holds for why A equality times y prime is less than or equal to B prime as well. And okay, so since lambda and 1 minus lambda are positive, and we've just established an upper bound on both A equality x prime and A equality y prime, then we have an upper bound on the entire thing then. So this entire sum is less than or equal to lambda times B equality plus 1 minus lambda B equality. I just replaced each of these things with their upper bound of B equality, and that upper bounds the entire thing. And so, and then you can just see that the lambda B equality and the minus lambda B equality cancel, and you're just left with B equality at the end. But that's what we started with. We started with B equality, and we ended up at B equality. So actually that means that everything, so this implies that everything in the chain they're all equal to constraints here. So in particular, this less than or equal to constraint, or thing that we established, we know that it's a less than or equal to, but in fact it's an equal to, because we started and ended with the same thing. And so that means that I'm just rewriting that constraint then now, replacing it with the less than or equal to with an equal to. And so we have that lambda A equality x prime plus 1 minus lambda A equality y prime is equal to lambda B equality plus 1 minus lambda B equality. So we know that this is true, but on the other hand, how can this be true? Well, the only way that this can be true is because lambda and 1 minus lambda are positive, so the only way to actually attain this upper bound is for each of a equality x prime and a equality y prime. They each individually need to obtain their upper bound of b equality. That must happen in order for this whole thing to obtain this upper bound here, and we know it does because we started and ended with the same thing. So that must mean then that a equality times x prime attains its upper bound of b equality, and the same thing for y prime. A equality times y prime also equals b equality. So that, this comment is just reiterating that. So yeah, otherwise the less than or equal to, this less than or equal to in the chain couldn't have attained equality, but it did because we started and ended with the same term, and so yeah, so we're able to deduce this then, that a equality x prime equals b equality, and a equality y prime equals b equality as well. But we're assuming, remember, that the rank of this matrix A equality is equal to n. So so that, in other words, this matrix A equality has full column rank. So all the columns of A equality are linearly independent. So how could we? So since they're all linearly independent, that means that there is a unique solution to the system A equality times x equals b equality. X here, it's not x bar, it's not x prime, it's just the variable x here. So A equality times x equals b equality. There is only one solution to that because we are assuming that the rank of A equality is n. So all the columns are linearly independent. And we already know what that solution is. It's x bar. X bar is the unique solution to this system. So actually, but on the other hand, x prime, we just showed that x prime and y prime are also satisfying that as well. So that actually must mean then that x bar is equal to x prime and y prime. So yeah, it's because there's only one solution. We have that these things, they're all the same thing. And in particular, x prime equals y prime. But that is a contradiction because we originally said that x prime and y prime must be distinct because x bar lied strictly between the line segment generated by x prime and y prime. But in fact, they're the same point, and it's also equal to x bar. So that entire thing is a contradiction then. Because these are supposed to be distinct things, but we've just shown that they're not. And so that all came about by us having assumed that x bar was not extreme. Then we got this whole chain that gave us a contradiction. So in fact, x bar must have been extreme then. So yeah, so if the rank of A equality is n, x bar has to be extreme because the columns of this matrix are linearly independent, so there's only one solution. Anyways, the method we just outlined shows this. So that's the first direction. So we just showed that if the rank is n, this is extreme. Now we need to go in the other direction, show that if x bar is extreme, that the rank of A equality is actually equal to n. So that's the other direction here. So if x bar is extreme, then the rank is n. So we're actually going to show the contrapositive of that, which is equivalent. So if the rank of A equality is strictly less than n, then we're going to show that x bar is not extreme. Remember, the rank of A equality is at most n because there's n columns of A equality. So it couldn't have been more than n. So if it's not equal to n, it has to be less than n. Okay, so this is what we'll show then. So we already showed that if the rank is equal to n, then x bar is extreme. Now if the rank is anything less, then x bar is not extreme. So why is that? Well, if the rank of A equality is strictly less than n, that means the columns of A equality are linearly dependent this time instead. So so that means that there's some vector d in Rn, and it's not 0. It's not the 0 vector. There's something else, such that A equality times d equals 0. So in other words, there's some non-trivial vector d in the null space of A equality. Okay, so that d will become relevant right now because we're going to construct points x prime and y prime using this vector d. So take epsilon to be some arbitrary positive constant and construct x prime and y prime by basically you're just perturbing the point x bar. So you go x bar and you go plus epsilon times d, and y prime is x bar minus epsilon times d. So you're imagining epsilon is probably going to end up being some pretty small number. And then d, but it's positive, strictly positive. And then d being non-zero means that you are moving in some direction. So x prime and y prime are distinct. Okay, and so the idea is that this choice of x prime and y prime will demonstrate that x bar lies strictly between these 2 points, x prime and y prime, and that will show that x bar is not extreme. That's what we want to show. And just at a glance, oops, sorry about that. At a glance, it seems like it's automatic because x bar is 1/2 x prime plus 1/2 y prime, right? That's just straightforward. You can just calculate that. So why is that? Why is that not showing, the result? Well, so what this shows is that x bar is strictly contained in the line segment from x prime to y prime. But what we need is not only does that need to be true, but we also need that x prime and y prime themselves are also inside the polyhedron. We know that the polyhedra are convex, so that if x prime and y prime are inside the polyhedron, then the line segment from x prime to y prime is also entirely contained in the polyhedron. That's by convexity of polyhedra. But first, we need to establish that x prime and y prime are themselves inside the polyhedron, and because that's what will show by definition that x bar is not extreme. So we do know that x bar is strictly contained in the line segment from x prime to y prime. Now we just need to show that that line segment is in fact inside the polyhedron. Okay, and so that's what we'll do. So we need to show that x prime and y prime are in the polyhedron for sufficiently small epsilon is the idea, because if epsilon is very, very small, then x prime and y prime are not very far away from x bar. And if x bar is in the polyhedron, then points not very far away from x bar should also be in the polyhedron. That's the idea. So we'll see what we need to take epsilon to be, but so the goal is to show that x prime and y prime satisfy being in the polyhedron, which means that they satisfy all the linear inequality constraints given by ax less than or equal to b. So first, let's just note that that a equality times x prime and y prime, so x bar plus or minus epsilon d, the plus or minus accounts for both x prime and y prime. So if I take a equality times that's just distribute a equality inside, and you can just see that d is in the null space of a equality. That's how we define d. So this part goes to 0 and it just vanishes. So plus or minus 0 actually doesn't matter then. So all we're left with is a equality times x bar, and we already know that that equals b equality by definition. So what we just showed is that a equality times x prime and y prime are equal to b equality. Specifically what that means is that for the constraints that were tight for x bar, those constraints are actually also tight for x prime and y prime. But more importantly, what really matters is that they just satisfy those constraints. Okay, so there's a whole bunch of constraints that x prime and y prime have to satisfy. It's all the linear constraints. But we've shown that for the constraints that were tight for x bar, x prime and y prime also satisfy those constraints. Whether or not they satisfy them with tightness, it's true, but it's less relevant. It's just what matters is that they just satisfy them at all. So here's my little picture at an attempt of what we're going for here. We have the overall system is ax less than or equal to b, right? And the green highlighted ones, those are supposed to be the ones that are tight for x bar. And what we just showed is that for those particular constraints, x prime and y prime both satisfy all those tight constraints, because a equality times x prime and y prime equals b equality. So it's less than or equal to specifically, or more generally, I guess. But so all those constraints, the ones that were tight for x bar, we've satisfied those then for x prime and y prime. So in order to show that x prime and y prime are in the polyhedron, we need to show that they satisfy the rest of the constraints. So for instance, I've highlighted another constraint, which is orange, put a question mark here because we don't know. How about for a constraint that's not tight for x bar? Does x prime and y prime satisfy that type of constraint, the type that's not tight for x bar? So that's what we still need to show. We need to show that for any constraint that's not tight. So here's what we need to show. So let us take a particular constraint of the overall system that is not part of the system A equality x equals B equality, right? So in other words, just not one of the green highlighted tight constraints. So we've accounted for the tight constraints for x bar. What we need to account for is just all the rest of the constraints now. So we know that whatever constraint we're taking now is not tight for x bar, and so that's what this particular constraint will be. And now let's show that if we plug in x equals x prime and x equals y prime, then for both of those points, it's still less than or equal to bi. Okay, so what is x prime and y prime? Oops, sorry. There we go. So what is x prime and y prime? Let's actually just do x prime because plus and minuses are just going to clutter notation a bit more than normal, but it doesn't matter. I mean, y prime is exactly analogous to x prime, just the same reasoning holds. But anyway, so let's just do x prime here. So it's x bar plus epsilon d. That's what x prime is. So if I take this constraint times x prime, well, this is what x prime is. It's x bar plus epsilon d. So I distribute the row I of a inside. So I get rho I of a times x bar and plus epsilon times rho I of a times d. Okay, and so what we're using now is the fact that this constraint is not tight for x bar. So what we know then is that rho I of a times x bar is strictly less than bi. Because we know that x bar is feasible, so it satisfies all the constraints, and it satisfies them all with less than or equal to, so either strictly less than or exactly equal to, and we're dealing with a constraint that is not tight now, so that means it must be strictly less than. So then we have that this quantity here is strictly less than bi, and then we just have this remaining part right here, epsilon times rho I of a times d. And remember, we haven't actually chosen what epsilon is yet. The idea was that it was supposed to be small, but this actually shows that it will be something kind of small because this quantity, I have no idea what rho I of a times d is. It's just going to be some number that I can't control in the slightest. But epsilon is a scalar in front of that. And so we're going to take epsilon to be something very, very, very small so that this entire quantity becomes something pretty close to zero. Because this is strictly less than bi, this part. So we have some slack left over because we need the entire thing to be less than or equal to bi. So if we have some leftover remaining part when we do rho I of a times x bar, then just shrink this quantity down small enough so that when you add it to this part, the overall thing is still less than or equal to bi. So you just take epsilon small enough to satisfy that, and of course you can, so just do that. Take epsilon to be something that works. So then that means that this overall quantity will be less than or equal to bi for epsilon that's sufficiently small. And so that's for any particular constraint that was not tight for x bar. And so that means that for an arbitrary constraint that's not tight, that this is true then. So we've accounted for the constraints that are not tight and for the constraints that are tight for x bar. So that's all the constraints then. And so then that means that x prime satisfies all the constraints. So so for any particular constraint rho I of a times x bar plus epsilon d, which is x prime, is less than or equal to bi for every index I from 1 to m for all rows. So for the rows that were corresponding to tight constraints, it just came automatically. We didn't need to do any of this work. And for the constraints that are not tight for x bar, you just take a small enough epsilon, and then overall you just pick the smallest of all those epsilons because that will work for all the constraints, right? It might be a different epsilon for each individual constraint that we analyzed in this way, but at the end of the day, it's just a finite number of them. So just take the smallest of those, and that'll work for every constraint. Okay, and so we have that x prime satisfies each individual constraint. So in other words, a times x prime is less than or equal to b, or in other words, x prime is in the polyhedron. And then the same reasoning shows that y prime is also in the polyhedron. The only difference between x prime and y prime is that you're going to have a different sign. It's going to be x bar minus epsilon d, but nothing will go wrong because it's still rho I of a times d. This part is still going to be some number. It might be positive, it might be negative. We really have no idea. But if it's negative, then when you add a negative number on it, this was already less than bi, then something negative on top of that is definitely going to be less than or equal to bi. So you don't have to worry about any minus signs here. You just have to actually worry if this is a positive quantity, and we don't know plus or we don't know whether it is or not. But even if it is positive, just taking epsilon small enough makes that work. So anyway, so yeah, so the exact same reasoning then. Wow, sorry, just going all over the place here. Yeah, the exact same reasoning shows that y prime is in the polyhedron. So both x prime and y prime are in the polyhedron, and the polyhedron is convex. So so then the entire line segment is contained in the polyhedron, and so then that shows that x bar is strictly contained in the line segment between x prime and y prime, because it was a half x prime plus a half y prime. And so that's the midpoint of x prime and y prime, in fact, and so that shows that x bar is not extreme. So we found a line segment inside the polyhedron that strictly contained x bar. So yeah, so that's why if the rank is strictly less than n, then you have some null space vector d that you can use. And null, or I'll just call it a null vector d that you can use, and you can travel in that direction. You can perturb x bar in the direction of plus and minus d, and in that direction, if you perturb it like that, if you perturb it small enough in that direction, the point x bar can be realized as the midpoint there for that line segment, and that line segment will be entirely contained in the polyhedron. So let's just let me say that again, basically, in the context of this example that we had before. Remember, x bar, the point 0, 1, we said it was not extreme. And we could visually verify that it was not extreme, and we showed by the test that we just proved that it's not extreme. So what's the reasoning behind the test that made this not extreme? Well, what happened was that when we took our A equality matrix, it was not full column rank. The rank of this matrix was strictly less than the number of columns. It was rank 1, and so because all the columns were, because it had too small of a rank, then there was some vector d in the null space of A equality. And so, for instance, here you can see that A equality, it's minus 1, 0. We already said that above. And so an example of a vector in the null space of A equality would be this vector, d being 0, 1. And so that would be this red arrow kind of, this is the direction of d. So we can travel in a null space direction, and we just scale it by some sufficiently small epsilon. And if you scale this vector d by a sufficiently small epsilon, then this entire line segment, you just perturb x bar up and down in the direction of this null space vector d, and this entire line segment will be contained in the polyhedron. And because of that, because you perturbed up and down, then this point will that you started at will be then strictly contained in that line segment given by x prime and y prime that you just created, and that's why x bar is not extreme by this test, because when A equality doesn't have a large enough rank, then you have a null space direction d you can travel in, such that if you perturb the point, that point will be in the middle of that perturbation, and that entire perturbation is entirely contained in the polyhedron. Okay, but what happens? So that reasoning is going to apply for every point along this line segment. We can always, if for any point along this line segment here, the same exact constraint will be tight, right? We're staying on this edge, so it's the same tight constraint. It's just one, so A equality doesn't change as long as you stay on this line segment, and so then the null vector D still works, and you just scale epsilon to be small enough, and if you just perturb just a little bit, then then that then that point on the edge um, will always be strictly contained in the line segment. But that fails once you finally hit a corner point here, because once you finally hit a corner point here, what happens to A equality? Then there's another tight constraint, and so A equality adds on another row. You've stayed on this edge, so that constraint stays there, but now you add on another tight constraint because you've run into another edge here. So you're at this corner here, and so A equality, once you hit this point, will become, this point right here will become 2 rows, and it'll be rank 2. And so now the rank is too large for us to have a null space direction D to travel in. And there isn't any vector D anymore that works. And so that's, by the reasoning of this proof, that's why this this will no longer work, and we'll no longer have a perturbation that we can use to show that this point is a midpoint. It is just strictly contained in any line segment, because in fact it's not. So yeah, so that's what happens. Travel up, 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 and then once you hit this next edge, you're now at a corner. A equality adds on, it gets a bigger rank, and now there's no null space direction to travel in. So yeah, so that's the reasoning for all this. So that's the proof. So we started by defining extreme points, and then we characterize extreme points in terms of the matrix of tight constraints, specifically the rank. If the rank of that matrix is the same as the dimension of the space we're working with or not, and then we proved that, and then we just kind of looked with a new perspective on this same example from before using that proof, and that's what happened in this video. So that's everything about extreme points. Basically, we're now going to use this this characterization of extreme points in terms of tight constraints to establish the relationship between extreme points and basic feasible solutions. But that will be coming up in a future video. Anyway, so that's it for this video at least. So thank you for watching.